Greetings, Saintsmen. We're going to start on lesson 5.1. I know that you're probably anticipating after going from chapter 3 that we would be in lesson, uh, this would be lesson chapter 4 next, but that is not the case with where we're at. Instead, we ended up skipping that entire chapter because it is transformational geometry, and that's stuff that's we're going to pick up along the way as we do this course. So, today, we're going to talk about how we classify triangles. First thing we're going to talk about is that we will do it by angle. All right. And yeah, let's actually move this over here to the right in this column. So there's three types of triangle. They're the same as the three types of angles, and that we have acute triangles. Um, oops, let's see here. I don't know how to get this next. Oh, here we go. Obtuse and right. So those are three types of angle in addition to our three types of triangle. So um, when we have an acute triangle, thinking about this, that we have all three angles within the triangle are acute. When you have the obtuse triangle, we have one obtuse angle, but by definition, we do have to have two other angles, and they both have to be acute. And on the right triangle, we have one right angle, and then we have two acute angles. So no matter what, when you have a triangle, you're going to have acute angles within it. All right. So there's that. Next, we can classify triangles by side. So we can classify by angle. And then here's how we do it by side. Oops. It's gracious. We first have the scalene triangle, which there are no sides that are congruent. We then have the isosceles triangle, which at least two sides are congruent. And the last we have is equilateral, which also is equiangular, which means that all sides are equal. All right. So scalene, they're all different. Isosceles, they are isosceles. They have at least two sides are congruent. So does that mean that an equilateral triangle is also isosceles? It does, and that's going to be important for how we define these things later on, because it means the properties we have for or for equilateral will also apply to. I'm sorry, for isosceles will apply to equilateral. So we're going to classify the following by side. So we're going to have a coordinate plane. We're going to graph a triangle. We're going to classify the triangle, and we can just put mini triangle rather than writing the entire word, ABC by side. So that's our notation. When we're talking about the triangle, we never actually write the word triangle. There's no reason to. So we have the coordinate A, which is going to be 0, 3. We have B, which is 7, 2, 3, 4, 5, 6, 7, 1. And then C, which is 1, -1. All right. I'm going to connect the dots here. And when we connect all those coordinates, we have a triangle, right? 3 line segments. That creates our polygon. So in order to do this, we need to deductively prove each side length. We're not just going to eyeball it and say, oh, this looks like it's scaling. So what we have to do here is we have to calculate 3 different distances. So we're going to calculate the distance of AB and see if any of these match. Okay, now here's where we're not going to simplify our radicals, because it kind of just creates more work for us. We can just see if these things match once we're done with the distance formula, even if it's not simplified. So we have 0 minus 7, difference of the x's squared, plus the difference of the y's, 3 minus 1. All right, this is going to give me the square root of negative 7 squared plus 2 squared, which will give me rad 49 plus 4, which ultimately is rad 53. Next, we have BC. Okay, so let's take a big square root. BC, we have, right, B and C. We have 7 minus 1 squared plus 1 minus minus, or plus 1 squared. So 7 minus 1 is going to be 6 squared plus 1 plus 1, which is 2 squared, which is going to give us rad 36 plus 4. So rad 40. Now go back to our definitions here, right? We're going to identify this thing. And right now, we don't have any sides congruent. We need at least 2 congruent. So for sure, this back up here is not going to be equilateral, okay? Because if all sides were equal, at least these first 2 would be. Last but not least, we need to do AC, right? It's a triangle, so it's the third one. It's this coordinate, all right? Let's do a difference of our x's and y's. So big square root again. We have 0 minus 1 squared plus 3 minus minus 1 squared, which is equal to negative 1 squared plus 4 squared, which is going to be equal to 1 plus 16, or rad 17. So none of these match, meaning that this has to be scalene, right? Okay. Theorem, and we're going to prove it. But here's what I'm going to give you in first is that we have the sum of the interior angles of a triangle is 180. Now, in class, I've tried to give it to you guys that effectively, where you're always going to use proofs is in every single math class you're going to take from here on out. Everything's going to be done via proof, right? Even when you get to algebra, right? All the lessons are effectively proofs showing you that these theorems all work, okay? You have some sort of new rule algebraically speaking. So here's what I'm going to do here. I'm going to construct this. So I have lines x, y parallel to BC. And what we're going to prove here is that the sum of all these angles for this triangle, and this triangle is A, B, C. This was X, Y. This is this parallel line. So I have this triangle ABC. So I construct this in a way so that the line going through A, which is XY, is going to be parallel to BC. And we're going to show that angles A, or BAC, angle C and angle B, have a sum of 180 degrees, because that's what the sum of all the interior angles should be. Now, you've probably been told this before. The sum of the interior angles, or people will say the sum of a triangle. What they mean is the sum of the interior angles of a triangle is equal to 180 degrees. And people just be like, hey, sum of a triangle is 180. That's great. But the question is why, right? Is it just something, there's no postulate, right? We need it to be given more. So here we go. Let's do our proof. So our given, our reasons, I'm sorry, our given, our reasons, our statements, yikes. Reasons. And what was given to us is we had triangle ABC, and that we had XY, which was parallel to BC, okay? And this is what we were given in our diagram. So, we should know that angle 1 and BAY, these two angles are going to be supplementary. And the reason why is they're a linear pair. okay? Which means that if we add the two together, it would equal 180, okay? So that's just the definition of supplementary angles. So now we can construct BAY, right? BAY is made up of two angles, which is angle 2 and angle 3. And that just means that the reason we got this is we just put two angles together through angle addition. It's the angle addition postulate, okay? Now, what we're trying to establish, because what we don't do is we don't do this whole thing with like three angles are supplementary to each other, all right? Um, so what we do instead is we're going to do this. We have this angle B, okay? And what I'm trying to show is that this angle, and this angle are supplementary, or are equal 180, right? And we already have the supplementary angles relationship with 1, and then really 2 and 3. So what I really would like to show is, because 2 is reflexively congruent to itself, we need to show that angle 1 and angle 3 equal these two angles. Well, guess what? We can, because we constructed those parallels, meaning that 1 and B, right, are two parallel lines cut by a transversal, meaning they are alternate interior angles. So we can say that angle 1 is congruent to angle B, right? And then angle 3 is congruent to angle C, because these are alternate interiors, right? This is congruent to this. This is going to be congruent to this. All right. So we can substitute, because we know BAY, right, is really 2 plus 3. So we can say angle 1 plus angle 2 plus angle 3 is equal to 180 because of substitution. Which we already know angle 2 or angle 1, we can substitute, right, with angle B. And then plus angle 2. And angle 3, we can substitute with angle C. All right. And then effectively, through the commutative property, we could actually show, right? Which we don't even need to do that. We can just say that we have this plus this all equal 180 degrees. Okay. So I could change the order of them if I really wanted to, but I don't really need to. So I've effectively proved my point, which is that the sum of all those interior angles is 180. All right. Now, new theorem, which is the exterior angle theorem, which I will explain to you guys because it's pretty quick. Okay, it's this. If I have angles 1 and 2 and 3, all right? And this is the exterior angle theorem, which states this. We have angle 1, which is referred to as a remote interior angle. Now think about this. What do you, when you're, I think some of you guys maybe don't know how to turn your TV on and off without the remote control. Like you don't know right now off the top of your head where the power button is on the TV across the room. Like you could find it, you could walk over, but if you had to find it in, you know, 1.5 seconds from seeing the TV, walking over to it, you probably know you'd look at the bottom and the back and wherever, but like your life depended on it, it'd be pretty sketchy, right? To find that. Instead, so some people, if you've lost the remote to the TV, it's common like just like the TV just doesn't work, right? Which is kind of a funny thing. So this is really critical. The reason why we do this is the remote, right? Because we have angles 2 and 3. The remote is that for the thing that's we use for the thing across the room. So angle 1 is not only just an exterior angle, but this is a remote exterior angle. Ugh, gosh. Okay, which means, I'm sorry, this is an interior angle. this is an exterior angle with angles 2 and 3 being remote interiors because they are across. Right? It's like you sitting in on the couch trying to zap, the TV across the room. Okay. So what it says is that the exterior angle in this theorem is equal to the sum of the remote interior angles. And here's why. It's actually not that crazy to think of it. Remember what we said is the sum of all three, the sum of all three of these of this angle right here, right? All these interior angles is 180. Now think about this. This guy is the missing angle right here, right? Now, what's the relationship between this guy and angle 1? Well, they're supplementary because they're a linear pair. Okay? So which means that these two, right, added together with this guy is also going to give us 180. So 2 and 3 together have to be equal to angle 1. It's actually a pretty quick proof, which we could do, and we will do. So let's do a little problem. Some fun one. Diagram here. Let's pretend like our line segments are straight. P, Q, R, S. And we're going to find the measure of angle PQS given the following. That this right here is 3x plus 25 degrees. That's PQS. We have 65 degrees for angle S, and angle R is 2x. Okay, well, think about what our theorem said. It said that that 3x plus 25, the exterior angle, was equal to the sum of the two remote interiors, 65 plus 2x. Okay, so let's solve. So you subtract 2x from both sides. So I have x plus 25 is equal to 65. Subtract 25 from both sides. So x is going to be equal to 40. Now, we're going to take this x, and we got to put it in here because it wants the measure of this angle. So the measure of angle PQS is equal to 3 times x, which is now 40, plus 25. 3 times 40 is 120, plus 25, which is going to be equal to 145. Excellent. Last thing. We have what's now called a corollary coming up. So we've dealt with definitions, properties, postulates, and theorems. And here's our corollary, which also is something that we can utilize for proof. So a corollary is going to be just a simple statement or truth that we take from a theorem. It's like the postulate of a theorem, if that makes sense. So we're going to say the measure of one acute angle of a right triangle is 1.5 times the measure of the other acute angle, and find the measure of each acute angle. So here's our corollary. You guys ready? I'm remembering what I just said a corollary was. It's a statement taken as a simple truth from a theorem. It's almost like a postulate that, it's not a postulate that's on its own, but given some theorem that we've proven, we can take some sort of like self-evident truth right off of that. So here's one for you, right? Here's our corollary. We have triangle ABC. What type of triangle is it? It's a right triangle. So in our right triangle, angles B and C have a sum of 90. Therefore, they're complementary. In a right triangle, the two acute angles are complementary. Okay? So, let's do our problem. The two angles, we have 1.5x plus x. And that's going to be equal to 90, right? 2.5, right? Because it's at 1.5 times. 2.5x is equal to 90. We divide by 2.5 on both sides. And x is going to be equal to 90 divided by 2.5. Okay. Now, 2.5, why would I do that? That's crazy, guys. 2.5 is really 5 halves. Ah, aren't fractions great? I think it's a lot easier for me to do. Factors, 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 factors. X is equal to factors, factors. 90 divided by 5 is 18, so 18 times 2 is 36. That's one of the angles. The other one is going to be 1.5 times 36, which is equal to 54, which you also could have just done, right? 90 minus 36, which is 54, because we knew they were going to be complementary. All right. And there you have it, guys. Good luck with your assignment.